So module 3, recursive algorithms. So this module, so we will learn very important algorithms we use to solve computing problems. Yeah. I think you all have experience about recursive algorithms, but we need to study some theoretical properties of recursive algorithm. Then we need to learn how to use recursive algorithm to solve computing problems. All right. 8.8, Part A, Introduction to Recursive Algorithm. 8.1, First View of Recursive Algorithm. Yeah. All right. We need to, so here, if you do not have training in recursive algorithms, you may not feel comfortable applying recursive algorithms. So you need some training. Okay? You need a recursive thinking in order to apply recursive algorithms to solve some relatively hard computing problems. Usually, when we solve relatively hard computing problems, we apply recursive algorithm. Easy problem, yeah, easy problem. Although you can still use recursive algorithm, but it may not be a good idea. Yeah, so you will see why. Yeah, so yeah, sometimes if you use recursive algorithm, it may not be a good idea. Yeah, so we need to learn that. Why recursive thinking is important in problem solving. Yeah. The main reason, okay? So this special type of thinking can help us solve the problem gradually. Remember? Gradually, okay? Step by step, gradually to solve a relatively hard computing problem. Yeah. So that's the power of this kind of thinking. Yeah. All right. Some problems can be solved both non-recursively and recursively. Okay. Yeah. Yeah. So you have two ways to solve. Now, the first way, we do not apply recursive algorithms. We use the non-recursive way. Yeah. Yeah. So non-recursive way, typically people call iterative way. Yeah. Iterative way. Yeah. So we will compare these two methods. Yeah. Advantages and disadvantages. Yeah. Power of recursion. That's the main reason. Why we use recursion? Because it's very powerful. Yeah. That's the main reason we use recursion. So powerful. Yeah. 8.2, I will use a simple example to show its power. Yeah. All right. Some relatively hard problems can only, because that means arguably, because our textbook said all problems can be solved using a non-recursive algorithm. Yeah. But extremely hard. We don't know how to solve it. Yeah. Theoretically, it could be solved by the non-recursion way, but extremely complicated. So we don't want to take that away. Yeah. All right. Can be solved by recursion. So then, in that situation, yeah. So we want to use recursion to solve. Yeah. All right. Now let me compare these two methods. Yeah. The first method, iterative. Second, recursive. Yeah. Advantages, disadvantages. Yeah. So then, when you solve a problem, you can choose. Okay? Yeah. In some situations, you need to choose the iterative way. In some situations, you need to choose the recursive way. Okay? All right. Less resource. Yeah, so that's an advantage, right? Iterative way property, it uses less resource. What resource? Memory resource. Yeah. Computer, main memory. You need to use resource, right? In the main memory. Yeah. How much space is allocated to your program, right? Allocation, space allocation, memory space allocation. So we're talking about that kind of resource, okay? Yeah, memory resource. All right. Harder implementation for hard problems. Yeah. So this is for hard problems, okay? Because for easy problems, yeah, it's not harder. Yeah, hard problems. Yeah. Non-recursive way could be very complicated. Yeah. In 8.2, in our 8.2, I will show you one example. We need to use recursion. After we solve the problem, you can think about, can you solve it using the iterative method? Yeah. Impossible. Okay? Impossible. Recursive, more resource. See? Yeah. So if you compare using computer memory resource more than the iterative way. Okay? If the same problem, you can implement it in both ways. Recursive way, iterative way. Recursive way will use more memory resource. Why? I will explain. Yeah. Why? Yeah. That's the cost. Okay? Nothing is free, right? Yeah. Recursion, powerful. Yeah. It's a powerful tool to solve computing problems, but there is a cost. You need to pay relatively high computing memory resource to get that power. Yeah. The trade-off. Yeah. But an easier implementation. We use recursion. Yeah. We have a recursive formula. Yeah. So we develop our recursive function. We call our functions recursively. Then we get a solution. Yeah. So easier implementation. Yeah. All right. Now let me explain why it uses more resource. Yeah. All right. Think about how does a computer programming language implement recursion? Yeah. Higher level programming language. Yeah. Okay. Java, Python, C++, they all support recursion, right? Yeah. So modern high level language just all support recursion. But those people who create these programming languages, in order to support recursion, they need to set up, they need to, create some internal mechanism to support it, right? Yeah, internal mechanism. So let me explain the idea of that internal mechanism for supporting recursion. Yeah. All right. How to make a function call itself, right? No, recursion. A function can call itself. Okay? Yeah. So that's a typical way we use recursion. How to make it happen in a programming language? Okay? Yeah. You need to do something, right? Yeah. Yeah. You need to do something special. There is some special algorithm built in the programming language. Yeah, so we need to understand that idea. So what kind of special algorithm is used to support, to make the recursion happen? Yeah. Let me draw a simple diagram to show you that idea. First, we need to use a special data structure. Okay? Yeah. This algorithm relies on a special data structure. Very simple. So you see, I draw this shape. It's some data structure you can guess. Stack data structure. In your data structure course, 2250, you'll learn several basic data structures. Stack, queue, linked list, right? Yeah, think about the stack. Here we use stack. Stack has some simple property. Do you still remember what is the main property of a stack data structure? Property. Yeah. Stack. Okay, all right. Okay, can you say again? I couldn't hear.
Last in, first out.
Oh, great. Yeah, yeah. Can you tell me your name? Your name? Robert? Is it?
Yes.
Oh, good. Okay. Yeah. Yeah. Robert says, last in, first out. Do you remember that? Yeah. Okay. Last in, first out. L, last in. I, first out. FO. That's the main property. Okay. Yeah. You push the items into the stack. The last in, you push to the bottom, right? The last in, yeah. Last in on top, right? Yeah. Last on top, right? Yeah. First at bottom, right? First at the bottom, okay? Yeah. But last on top, so first out. When you need to retrieve the item from the stack, you retrieve from the top. Yeah. So last in, first out. Yeah. So we use this property to implement recursion. Now, think about, we have a recursive function. Okay. Yeah. F of n. Yeah. In order to calculate f of n, yeah, because f of n, its value is not available, f of n relies on some previous value. Okay? All right. So here, let me assume a simple case. It relies on f of n minus 1. Okay? But f of n minus 1 relies on its previous value, f of n minus 2, and so on. Okay? Yeah. All the way down to the bottom. Yeah. That kind of recursion we need to do to calculate our function value, f of n. All right. Yeah. Now, let's use stack to implement this calculation. First function call, f of n. Not available. Its value not available. Yeah. So we search our, data collection. The function value is not available. Then we put it on hold, so we push it into stack. Okay. All right. F of n not available, so we push it into the stack. It's at the bottom. Okay. Then, because it relies on f of n minus 1, now let's call let's search the value for f of n minus 1. Still not available. Yeah. We push it into stack again. Yeah. So f of n minus 1, and so on. Okay? And so on. Right? Yeah. Push it. All right. Then we'll keep pushing. We keep pushing unknown values into the stack. Okay? But eventually we will reach known value, right? Because your recursive formula, you should provide base value, right? Base value. You need to have the initial values, right? Yeah. Otherwise, no solution. So when we reach the base value, it is known. When we reach the base value, it is known. Okay? All right. Suppose the top one is f of 1. Yeah. F of 1, suppose still unknown, we push into it. But when we calculate f of 1, it relies on f of 0, okay? But f of 0, as a base value, it must be given, okay? F of 0 must be given. Then we can calculate the function value. Now, so this time, we retrieve f of 0 to do the calculation. When we do the calculation, remember last in, first out. F of 1 is last in, right? Yeah, first out, we pop it out, okay? Pop out f of 1. F of 1 rely on f of 0, so f of 1 value can be calculated. After f of 1 is known, we pop out the next value in the stack, f of 2. Then we use f of 1 to calculate f of 2. So f of 2 is known. Then pop out the next one in the stack and make it known, and so on. Then, all the way at the end, we can calculate the last item in the stack, f of n. Then the value is found. Okay? This is the implementation, internal implementation of recursion. Okay? All right. Based on this understanding, you can see this stack stays in the computer main memory. Inside computer main memory, okay? Yeah. So it uses the resource. This part is the, compute main resource in the main memory. Okay? When the stack is very deep, yeah, because your stack could be very deep, then it uses a lot of computing memory. Okay? The deep stack uses computer memory. Yeah. But this iterative method, typically it's a loop. Yeah. For loop, while loop, it's a loop. Okay? Yeah. When we use for loop, while loop, loop way to implement iterative algorithms, we do not use stack. Okay? If we do not use stack, we only use a few temporary variables, right? Yeah. In each iteration, we use a few temporary variables, but in the second iteration, the old temporary variables can still be used, right? Reuse. So we do not need to use many computing resources. Yeah. Yeah. So in that way, if we only look at the computing resource, iterative method is much more efficient than recursive algorithm. Okay? Yeah. All right. Yeah. But that's the sacrifice we want to have in order to get its power to solve the hard computing, relatively hard computing problems. In order to get this power, okay? Yeah. So this is our investment, you can call. Yeah. Pay. We are willing to pay this much to get that big power. Okay? All right. Yeah. Based on this understanding, yeah. So later, so you will see. Yeah. Yeah. I don't know if you have some programming experience, right? Yeah, a little bit. Do you remember when you write some programs? Sometimes when you run your programs, you may have the runtime error called a stack overflow. Any of you, Stack Overflow. That's the runtime error. Okay? So what's that? Yeah. That's here. With this picture, you can understand why you get a Stack Overflow. Because your stack to implement recursion is too deep. And it is larger than your available memory resource. It's larger than you get overflow. Okay? When you get overflow, yeah, it's a runtime error. Okay? It's a runtime error. Yeah. Then your program terminates immediately. Stack Overflow. Okay? Terminates immediately. Yeah. Yeah. So with this understanding, yeah, now if later, especially when you run some big program, yeah, big program using recursion, and your data is large, yeah, so there is a possibility you get a Stack Overflow, runtime error. Okay? Yeah. So here we understand that kind of errors. Yeah. Yeah. Later, when we have more experience, you need to think about when this problem occurs, you need to think about how to solve it. Okay? Yeah. So in the future, yeah, when you work in the real world situations, you need to find solutions. Yeah. Okay? Yeah. So I will talk about this problem later. Yeah. All right. Then, now we want to learn recursive thinking. I want to use a simple concrete question to show you how to apply recursive thinking to solve real world, to solve a computing problem. Simple computing problem. Yeah. So not real. All right. Problem number 7, calculate the factorial. Yeah. Given a non-negative integer n, find its factorial. Yeah. First, this simple question, we don't need a recursion, right? Yeah. This simple question, we use a simple for loop. We can find its value easily. Yeah. But here, we use this simple example as some education, for education purpose. Yeah. So we want to learn the recursive thinking way. So we use this simple example to get started. Yeah. All right. Method 1. Yeah. Method 1, iterative way. Yeah. So this one, we just based on the definition of factorial. Yeah. So we use a simple for loop. Yeah. But when we apply a for loop, we need a initial value, right? Yeah. So we need initial value in our for loop. So here we make, this is our initial value. 0 factorial equals 1. Can you understand that? 0 factorial equals 1. Do you feel it makes sense? Why 0 factorial is not 0? It is 1. Can you understand? Why 0 factorial is not 0? It is 1. Can you see that? Yeah? All right? Yeah. All right? Yeah. So we need to understand that. Okay? All right. So here, let me, delay the explanation a little bit. Yeah. Yeah. All right. Okay. Yeah. Implementation. Yeah. Implement just one for loop. Okay. So I do not need to write it out. So you know how to do it. Yeah. Yeah. So we want to do it differently. In this method 2, we use the recursive way to do it. Yeah. Yeah. Recursion. Yeah. So we intentionally we make it recursion representation for this function. Okay? All right. Yeah. So here we practice some general problem-solving approach. Yeah. General problem-solving approach. Okay? divide and conquer. Yeah. So here we need to apply this divide and conquer approach. Yeah. So another very powerful methodology in problem solving. Divide and conquer. Yeah. Actually, our module 4, the title of our module 4 is divide and conquer. After we finish this module, recursive algorithm, then we will learn divide and conquer approach in module 4. Yeah. But here we need to use it. Okay? Yeah. So let's start early. Yeah. The problem easier when the size is smaller, right? When the problem size is smaller, the problem is easier. Okay? Yeah. So that's our experience, typical experience. Okay? All right. So we use this idea to help us in problem solving. Based on this is our observation. Based on this observation, yeah, in order to make our current problem easier, we want to reduce the problem sizes. Reduce the problem sizes. If we can reduce the problem sizes, we make it easier to solve. That idea. Okay. All right. Yeah. So when we work on problem of current size, yeah, but when we reduce problem size, a very important step in this recursive method is we assume that a problem of a smaller size has been solved. This assumption is special. In this recursive thinking, this step is special. Assumption.
That is the hard to solve the recursive process.
Yes, yeah. Yeah, typical recursive process.
You're taking a problem and just, doing the same problem, but on like mini problems that make up the problem.
Yeah,
I know
yeah.
that was uncomfortable, but like, let's just,
Yeah.
expand it for some of this process stuff.
Yes, yeah, yeah. All right, yeah. So let me continue this story, all right? Yeah. So assume the problem of smaller size has been solved. Yeah. So some people may ask, why you can assume? Yeah. Why you can assume? Yeah. Remember, we have base cases, right? We have known base cases at the beginning. Yeah. Because our base cases, that's the starting point. Yeah. That starting point, that belongs to this part, right? Yeah. Because that's the, early known solutions for very small problem size. Yeah. So we can start from there. After that, can we assume the problem has been solved? It's given, the solution given, right? Yeah. So we assume, no problem. After that, we have recursion to build up, right? Yeah. So this assumption has no problem if the base cases are available. If the base cases are available, then this assumption makes sense. Yeah. Yeah. Assumption, no problem. We can do it. Yeah. All right. Okay. Yeah. So then step 3, yeah, because you have a known solution with smaller problem sizes, then you want to move to the problem of the current size, larger, yeah. Then these two solutions, there is a gap between them, right? Yeah, there is a gap. Move from smaller problem size solution to a little larger problem size solution, there is a gap. Okay? So our step 3, you need to fix the gap through recurrence relation. You need to develop a recurrence relation to connect these two problem sizes. the solutions of these two problem sizes. Okay? Yeah. After you complete these 3 steps, yeah, all right? Yeah. So actually, you use 3 steps in our recursive thinking. Okay? 3 steps in our recursive thinking. Then you can solve this problem recursively. Yeah. So that's the idea. Okay? All right? Yeah. Now, let's apply this recursive thinking way on this very simple factorial example. Yeah. All right. First, we need to divide and conquer. Okay? When we start, we need to divide and conquer. How do we divide the problem? Okay? The problem size, the data, right? Yeah. Yeah. So let us give a function. Yeah. So we can refer. Yeah. We need to give a name to this factorial function. So let's call it capital F of n. Yeah. So then we can refer to it. Okay? All right. This is the way we divide. So we divide, we only chop off the last number. Yeah. That's the divide away. Okay? That's the size reduction. We reduce the problem size by 1, each time by 1. Okay? So that's one typical way. Okay? One commonly used way. Okay? Yeah. Later we don't have to divide by 1 every time. Yeah. Later we have, different ways to divide our data. Yeah. All right. After this divide step, yeah, remember our step 2, assume a problem with smaller size is known. Yeah, here we can assume, yeah, if the problem of this n-1 size is known, so we have this f of n-1 value available. Okay? Yeah? Yeah. If it is available, yeah, we can use it to represent our destination function value, f of n. Yeah. How to represent it? How to use a known old value to represent unknown new value. Yeah. So our step 3, we need a recursion formula. Yeah. This is our recursion formula. How to connect 2 solutions, f values in one recursive formula. Yeah. This is our recursive formula. Okay? All right. So with this formula, there we can implement our function using this formula. Yeah, you can write a program easily. Okay, implementation. Yeah, make it a recursive way. Yeah, all right. Yeah. But here, when we define factorial here, we need n positive, right? Yeah. We need n positive. Yeah. In our usual definition of factorial, our n should be positive, right? Yeah. 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 When n equals 0, it's hard to imagine what appropriate value we should use for 0 factorial. Yeah. It's hard to imagine, okay? Hard to imagine, all right. Now let's fix that problem. How to imagine, yeah, all right. How to see 0 factorial equals 1, yeah. Because you cannot use some random value here. You have to use the right one. Yeah. You need to use the right value. Yeah. Otherwise, you will get contradiction. If you use some wrong value for 0 factorial, sooner or later you will have some contradiction. Yeah. So here we don't want to have any contradiction. Yeah. So we need to find that right one, right value here. Yeah. All right, let me rewrite the recursive formula. Yeah. So this is the recursive formula. Rewrite it. Okay, f of n minus 1, yeah, just simple algebraic operation, manipulation. F of n minus 1 equals f of n over n. Yeah. Yeah. That should be correct, right? Yeah, because yeah, that's the, no contradiction in this step. Okay? Now, let us plug in the value. Yeah. So this formula is correct. Let us plug in n equals 1 into this formula. Okay? Yeah. N equals 1. Okay? When n equals 1, right-hand side has no problem, right? Right-hand side, no problem. Yeah. So let's just do it. Okay? So we get f of 0 equals f of 1 over 1. F of 1, that is 1 factorial. 1 factorial equals 1, you have no problem, right? Yeah. 1 factorial equals 1. Yeah. That's obvious. Yeah. So 1 over 1 equals 1. Then you see what you get. F of 0 equals 1. F of 0 means corresponds to 0 factorial, right? Based on our function definition. F of 0 corresponds to 0 factorial. Is it 0 factorial equals 1? Right? Is it 0 factorial equals 1? Yeah. Compatible. Okay? No contradiction. Yeah. So this is the way we understand why 0 factorial should be 1. Yeah. All right. Yeah. Yeah. So our conclusion, yeah. Although when we apply this recursive way to solve this factorial problem, it does not help in efficiency. Yeah, if you consider efficiency, actually this one uses more computing resource. Okay? Yeah. It is not as good as the iterative way. Yeah. Yeah. But what do we get? What do we get is this. At least we know it's some interesting way to solve problem, right? Yeah? Yeah. Yeah. Interesting way, because this problem is too simple, too easy. That's the reason we do not need to use a powerful tool to solve it. Overkill, right? Yeah, overkill to solve this easy problem. Yeah. Yeah, you need to deal with overflow. Yeah, that's a big problem. Right. Right. Yeah. That's the, So you do not have the benefit, but the potential problem is big, right? The overflow problem. Yeah. Right? Stack overflow. Yeah. So it's not a good idea. Okay? Yeah. So that's why I say, it's for education purpose, for understanding. Yeah. But in the real world, nobody wants to do it in this way. Okay? Nobody wants to do it in this way. Okay? All right? Yeah. 8.2. Now this time, I want to use one simple example to show you the power of recursive algorithm. That's the main reason we are willing to pay relatively high cost. Yeah. So that's not cheap, right? A lot of memory resource, that's not cheap. Okay? Yeah. But in order to get this power, so we are willing to pay that much. Yeah. Yeah. Now, let me give you the question. The question, puzzle problem, the Tower of Hanoi problem. Yeah. This is a puzzle problem. Okay? Yeah. So I think, you played this puzzle before. Yeah. Yeah. Let me describe this puzzle. There are 3 disks on the first peg. Okay. Now we need to follow certain rules. There are 3 rules we need to follow to move this stack of 3 disks in different sizes, in increasing sizes, from one peg, from the first peg to the third peg. Okay? Yeah. Follow 3 rules. I need to give you these 3 rules. The first rule, only one disk can be moved at a time. Yeah. Each time, you can only move one disk from one peg to another peg. Yeah. Rule number 1. Rule number 2, a disk cannot be placed on top of a smaller disk. You have to maintain the order. Okay? A smaller disk is always on top of a larger disk. That's the rule number 2. Okay? Rule number 2. Yeah. So, yeah. All right? Yeah. You have to follow. Okay? All right. Rule number 3, all disks must be stored on a peg except while being moved. So what's the meaning of that? Yeah. When you make the move, you cannot place a disk on the table. Okay? That's illegal. Okay? You cannot place any disk on the table. Temporarily, not allowed. Because if you can do that, then the puzzle is too easy to solve, right? Yeah. So in the move, in the air, it's okay. You move, the disk is in the air. But when you place it somewhere, you have to place it on one of the 3 disks, 3 pegs. Yeah, one of the 3 pegs, you can place your disk. Okay? All right. So when you follow these 3 rules, then this puzzle is a little challenging, right? Yeah, not too hard, but at least you need to try several times, right? Yeah, it is a little challenging. Yeah, yeah. So this is the problem, famous puzzle problem, Tower of Hanoi problem. Okay, all right. And other example I show you here, I use 3 disks, yeah. But our goal, we need to do it for n disks. Yeah. We need to solve n disk problem. Yeah. Think about how to solve n disk problem. That's not easy, right? Yeah. N is a variable. Okay. N could be 100. Imagine I have 100 disks. How to solve it? Overwhelming, right? Yeah, overwhelming. Yeah. But we can use recursive algorithm to solve it. That's the reason I show you it's powerful. Yeah. We need to use the power of recursion here. Otherwise, we cannot solve 100 disk problem. Yeah. All right. Yeah. Let's look at the, analysis. Yeah. How to solve the general problem with n disks. Yeah. So in problem solving, we need to use some strategy. Yeah. In this situation, we need to use some strategy. Yeah. And this strategy, I used a few times before. Can you connect to that strategy? Yeah, I used several times before in this situation. Yeah, yeah. When the problem size here, the problem size is n. When the problem size is relatively large, how do you get started? How do you get started? When the problem is relatively hard, how do you get started? Okay. Yes, great. Yeah. Great. That's our strategy. We do some experiments on the problem of smallest possible sizes. Okay? We do experiments using smallest possible sizes. All right? Yeah. All right. Let's start. Start with n equals 1 or 2, is that easy? Yeah, that's one disk problem, that's trivial, right? Yeah, one move, yeah, you're done. Yeah. It's trivial, okay? All right. Yeah. How about two disk problem? Two disk problem also easy, right? Yeah, on small disk, one. Top disk, you put it on the middle peg, okay? Then the bottom disk, the destination peg, right? Then move the, smaller disk to the destination peg. Yeah? How many moves? If we have two disks, how many moves? Top disk, bottom disk, then another move. 3 moves, right? Yeah, 3. Okay. Yeah. We need 3 moves to solve the problem. All right. Yeah. All right. So now, next, this time, we need to work on 3-disk problem. Yeah. And when we work on the 3-disk problem, we already have solutions for n equals 1, n equals 2. Yeah? So we can make our assumption. The problems of smaller sizes are known. Solutions are available. That means you can use the solutions. You can use the solutions for problem of size 2. You can use it. Okay? Yeah. So you only need to take care of the difference part, right? You only need to take care of the difference part. Yeah. So that's the recursive thinking. You only need to find a way to bridge the gap, yeah. The difference part. Yeah. Make a bridge. That bridge is the recursive formula. Recursion formula, that's the bridge. Bridge two adjacent cases. Okay? Case for n equals 2 and the case for n equals 3. Then you need a bridge to connect these 2 cases. All right? Yeah. Now, let's use this recursive thinking on problem size 3. It's non-trivial, so we need to do some work, right? Here, you need to do some meaningful work. Okay? Yeah. It's non-trivial. Yeah. All right? Yeah. So let us do our experiment explicitly from beginning to end. How about that? No. No. We need to do some hands-on work. Here, I do not have the, concrete puzzle to let you do here. Yeah. So let's do it on PowerPoint slide. Okay. Let's move our disks, on my PowerPoint slides. Yeah. Yeah. So here, let's do the moving. Yeah. Moving 3 disks. Yeah. So step by step to do the moving. All right. Our original setup, step 0. Okay. Get it started. First move. Yeah. Move smallest disk on peg 3. Yeah. Peg 3. Okay. All right. Move to the middle disk. Place it on the middle peg. Yeah. Yeah. Then after that, we move the smallest disk back to the temporary middle peg. Yeah. Then, because our destination, after that move, our destination peg is empty, so we can place the largest disk to our destination peg. Okay? All right. Yeah. Here you can see what we do if we use P represent problem. P of 2 means we apply the solution of problem of size 2. Yeah. Yeah. Size 2 solution. Yeah. Here, because we move these 2 disks to the middle peg, that is exactly we apply size 2 solution. Yeah. Size 2, move 2 disks from one peg to another peg. Yeah. Then step number 4, yeah, so the bottom disk, we move to its destination location. Yeah. All right. After that, step 5, yeah. After that, you can see what do we need to do. We just need to move these 2 disks on top of the largest disk on peg 3. Yeah. But when we do that, can you imagine we just apply problem of size 2 another time? Yeah. That's the solution of problem of size 2 another time. Yeah. All right. Yeah. So let's apply that solution. Yeah. Yeah. Move the smallest disk to first peg, then the middle disk to its destination location, then last step, the smallest disk on the destination peg. Yeah. Problem solved. Yeah. Here you can see we need to make 7 moves. 7 moves to complete the problem of size 3. Yeah. 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 Now, think about. Yeah. So you need to, because after you complete this experiment, you need to do some summary. Yeah. You need to do some summary. Okay? Yeah. Because your goal, you want to generate this idea to the general case, n-disk case. N-disk case, yeah, here, our experiment result. Yeah. We should be able to get enough information from this experiment result to extend it, to generalize it to the general n-disk case. That's the idea. So what do we need to do? Yeah. All right. Yeah. So what kind of summary we like to do here? Yeah. All right. In order to solve problem of size 3, so here, because we need to solve problem of size 3. Okay? Yeah. All right. Then what we basically do, yeah, we need to apply P of 2 first, right? Yeah. After P of 2, then we need to move the bottom disk. Yeah. Yeah. Bottom disk from its starting position to the end position. Yeah. And we need to make a 1 disk move. Okay? All right. After that, we need to apply another P of 2 solution. Yeah. So you can see, yeah, this is our recursion. Yeah. In order to do P of 3, we need to apply the solution of its previous problem size, P of 2, twice, right? Twice. But in between, yeah, we need to apply this solution twice. But in between, we need to move the largest disk, 1 disk move in between. Okay? That's the pattern, right? Yeah. That's the pattern. Yeah. This pattern, yeah, that's something like our recursive formula. Yeah. That corresponds to our recursive formula. Recursive, yeah. So this is our recursion. This is recursion. Okay? All right. All right. Next, we need to generalize. We need to do the general case. Now we are ready. Okay? Yeah. After, we understand the whole process. Okay? Now we are ready to move n-disk following the same recursion. We have that recursion, right? That recursion is important. Okay? So now we rely on that recursion to solve this problem. Okay? All right, let me show you how to apply the recursion. Okay? Yeah. After that, you can imagine without recursion how to solve the problem. Yeah. All right. Yeah. Yeah. So here, when we start, yeah, here, I just show you the main idea. Okay? Yeah, main idea. So when we start, yeah, but when we start this time, yeah, because for me it's a little hard to draw n disks. So here I still use the 3-disk picture, but we can imagine there are n disks here. Okay? Yeah. Stack of n disks. Yeah. We are working on n disk problem here. Yeah. But for n disks, we have 3 pegs. Okay? You cannot use more than 3 pegs. Okay? You can only use 3 pegs, following the rule. Yeah. 3 rules, same 3 rules. All right. Then, now we make a move, okay? Based on the recursion type of move. We can save a lot of words, yeah, based on recursion. Okay. All right. Yeah. To solve this P of n, first we need to apply P of n minus 1, right? Yeah. The problem, we need to apply the solution of the previous problem size. First time. Yeah. First time. Okay? All right. So we apply, yeah, the solution of the problem of the previous problem size. Yeah. P of n minus 1. Yeah, we apply it. Yeah. We assume it's available. Okay? We apply that solution first. Yeah. After that, in between, yeah, we will apply this problem twice. Okay? We will apply it twice. But in between, we need to move the bottom disk from the beginning peg to the destination peg. One move, one disk move. Okay? All right. One disk move. All right. After that one, then we apply another P of n minus 1. Okay? Yeah. Then we're done. Think about that. Then we're done. Okay? Yeah. Yeah. So here you can see, for this very complicated problem, when we use the recursion, it's not hard. Okay? Yeah. So let me implement this 3 steps, okay, using pseudocode. Yeah, pseudocode to write an implementation. Yeah. All right. Look at this pseudocode. Okay. Yeah. N disk moving pseudocode. Yeah, we define a function. Yeah. Here I use the C++. Yeah. Because this example I took from 2250 class. Yeah. I taught that class many years ago. Yeah. So I took from there. Yeah. C++ code. All right. Yeah. You need 4 parameters. Yeah. 4 parameters. The first parameter, the disk number. The number of disks. Okay? Yeah. Then 3 pegs, you use 3 different numbers represent. Okay? Peg 1, temporary peg, it's peg number 2, peg number 3. Okay? Yeah. So this is number of disks. Oh, corresponds to n. Okay? This corresponds to n. Yeah. All right. Then, yeah, if the disk number greater than 0, yeah, so you implement the 3 steps. You call this function recursively for the disk number n minus 1. Yeah? N minus 1. Yeah. Then you need to carefully, arrange the 3 peg numbers. Yeah. So beginning peg number 1, destination peg number 2, and temporary peg number 3. Okay? Temporary peg number 3. Okay? So you apply that. Then move your bottom disk. You just print out a message, show that you move the disk. Okay? Yeah. So that's the print out message. At the end, you apply another P of n-1. Yeah. There, but you need to arrange the 3 pegs differently. Yeah. The temporary peg number 2, that becomes the starting location of your n-1 pegs. Okay. Then destination, that's your real destination. 3. And temporary peg, that's your original starting peg becomes temporary peg. Okay? In that way, you implement this recursive function very easy, right? Yeah. The code, you only need a few lines. For such a complicated question, you only need a few lines. Then you solve it. So after this example, can you appreciate the power of recursion? Right? Think about if you are not allowed to use recursion, how can you solve the problem? How can you solve the problem? Yeah. Right? How can you solve the problem without using recursion? Yeah. I cannot solve it. Okay? Yeah. I admit I cannot do it. Okay? Yeah. So that's the power of recursion. Why we are willing to use so much memory cost, right? Yeah. The deep stack. Yeah. That's a lot of resource in order to make this happen because of its power. We need this power. Okay? All right, that's it.